Yeah, thanks. So, like, if you actually came for the Elm, like, you're gonna be really, really sad. Like, Alexi told me to, like, I needed to sex up my talk title, and I'm really gonna talk about functional reactive programming type stuff. But like, a lot of people have learned about that from Elm, so so that's the Elm part. So, spoiler, sorry, we don't get to have a pure script Elm fight. Like now, we can do that later or something. So my name's Oscar. Please follow me on the Twitter. They need all the active users they can get if you've been following the news. Or you can email me at Stripe. Sorry for the burn for my former tweet friends. Okay. So like, what's machine learning all about? Machine learning is really simple. It's about, like, you have like matrices like this, and it's like some beautiful ground truth about reality that you just you come by somehow. And you've got a bunch of columns and some rows, and you have something you want to predict. In this case, I want to predict X. So I've got some, some 0, 1, 1, 0, 0 on these features, and that's good, evidently, and then, it can be bad. So that's how we start with our ML. And like, all we have to do is, like, I'll give you this, and then what I'm going to do is, your job as a machine learning person is to produce some kind of function. On the right-hand side, it might, in this example, it's a tree. Many popular algorithms are tree-like. That we take this over here, and we somehow infer some generalizable function that's going to work over the same domain of inputs on the left-hand side. So if you've been hearing about machine learning, you think it's all hot, like, you probably think that this is cool, or and that arrow is really like the sexy thing. Like, how do we go from the matrix to the function? That's the thing you get really super pumped about. So I'm on a team called the Machine Learning Infrastructure Team at Stripe. So you think that I would be like worried about that, but actually I'm not at all worried about that problem. So because really we're worried about this problem, is where does this matrix come from? So that's actually, turns out, the hard part. Like, if I just give you the matrix, you can download TensorFlow or scikit-learn or anything and just throw it in there, and it's you can go win your Kaggle competition. But it's getting that matrix that is a really hard problem, especially at a company that's operating with a large scale of data or a diversity of data sources. So really, what machine learning is really all about is basically akin to this kind of job, where it's you've got a bunch of serialized data laying all around, probably inconsistently serialized, and you've got to somehow get it all together, collect it back, and turn it into one of those pretty matrices. And then it's pretty easy after that. So that's what this talk is going to be about. So what are the key challenges that we had to face, or we're still in fact facing? The main thing is that you have all these different data sources. Sometimes they're God forbid, mutable state in some database. Some might be log data sources that get published onto a Kafka queue. Some might be on the Kafka queue and put on disk somewhere. So how do we integrate all of those things together to produce that matrix of different rows that we can train on? So that's a big, big challenge. So has anyone else faced that challenge in their place of business or in their homes? Okay. The second one, this is one I could probably geek out about. It's probably already tipping my hand that I get more excited about the infrastructure side of it. But it's at Stripe, a big problem is a fraud problem. We're trying to predict fraud. Or at Twitter, maybe they wanted to predict clicks. So you're trying to predict a click. If you're not careful, if you're really if you don't do your job right, you can include in that matrix information about the future, as it were, because you have all this data from the past. You could accidentally leak back into it something that was caused by the click itself. And then an algorithm can learn extremely well whether or not things would be clicked because of this sneaking in information from the future. So you need to make sure never ever to do that in a predictive domain like fraud or click prediction. And that's not easy. It's if you just give someone go to town with Spark or MapReduce data flow type programming on batch data on disk, you have to be very careful to do these time-aware joins so that I've joined this data as it would have been viewed at that moment in time. This is a pain. Has anybody ever dealt with that pain before, or am I the only one who's dealt with that pain? Okay, so people, this is not, you know what I'm talking about. the next question is, how do we make sure the data with training is consistent with scoring? So you might have the luxury of doing batch scoring, and then it's not such a hard problem because you just run the same tool in batch to get the data to train, and then you can run that tool again and score, and like life is easy. But a lot of people, such as Stripe, we want to make a decision as to whether or not to process a payment. We need to do that like at a moment that an API call is made. It's really not very useful. I mean, it could be somewhat useful, but it's not nearly as useful if we have to do that later or something. We need to be able to do that in real time at the moment. So that means the models were trained like, some period of time ago. Let's not say how long ago. And they were done with batch compute. Now, if we inconsistently compute the data at real time, like we're gonna like totally goof that up, right? We're gonna send the wrong inputs in. That's bad news. So then the last thing is, well, if you solve this problem poorly, step 3, step 4 becomes really hard. How do we share code between the training phases and the scoring phases? Like if we have to write that code twice, like we have a good chance of having a bug, which increases the probability that we do have inconsistent data for training and scoring. So those are the kind of problems we set out to solve on this, and not just me, like my team, the whole team that I work with have been working on this for a while. So it turns out like there are some cool things in the functional programming community that are related to time. So usually you might think that functional programming is about immutability. That like off the top of your head seems like it's like anti-evolution in time, right? Because things tend to mutate as time goes on. But actually there's some really nice work on this, and I don't really actually know all the whole history. I've read some APIs over the years, some of the papers, and I think this was kind of like someone can correct me later if there was actually an earlier work than this. But I did find it weird that it was so focused on animation when I dug this paper up. But this was a paper by some well-known folks in the functional programming from 1997. And they introduce a model where they have events and behaviors, okay? So, and this was quite influential to, I mean, if you did know about Elm, they had a notion of a signal. If you looked at this in the past, in the earlier iterations of Elm, I think the latest iteration has done away with that. But their Elm signal is very much a behavior. It's very, very similar to behavior. So these are the main kind of methods re-expressed in like Scala-like syntax that you have available to these things. So like an event is basically just a tagged like value with a timestamp associated with it. And of course you can like transform like an event with time. That's pretty clear just based on its structure. Now a behavior is something that you can ask about it at a certain time and get a value. It's like a total function from time to A, okay? So that's what behavior is all about. We can pretty obviously lift any value into behavior. Like if I just want to be a constant, look, like 1, here's my behavior. I'm going to behave 1 from now on. Like that's a legit behavior because you just ask later what's the value of it. It's like 1. So you can do that for anything. But the cool thing is, and this is where it becomes like more useful, is that you can compose these in a somewhat interesting way. And it's like deja vu all over again when you go to a freaking Scala conference and you have to like listen one more time to like all the type classes, but we're gonna do it again. Here we go. So this is like one formulation of something like it's an applicative, right? So it's something weaker than a monad. Monad would be too much. So very often in life we actually want to restrict the power, right? So behavior is applicative. I can combine 2 together and imagine doing some function with them and making a new one. So what does this look like? This is actually a very, very natural thing. Signal is, signal, behavior, feature might be another way to think about this. So what does this have to do with machine learning? So I'm going to say like a feature. So feature in machine learning is basically just some kind of generally time-varying input into a model, okay? So that's just what we mean by feature. We could say input, you could say signal, whatever. We're going to use the word feature here. So as time comes along, like a feature has a value. But like for the purposes of the system we're going to describe today, those features can't change like at any moment in time. they change in reaction to some event happening. So event happens, here we go, here's E1, now feature has changed to take on a new value, and, and so on and so forth. So that's the kind of story we want to present. Like you can imagine, and I'll draw this again a few more times in this talk, that there's this curve going on, and that's really what our feature will logically represent. Okay? So back to our magical input, our magical matrices that we kind of like somehow have to come up with. That's kind of our goal. Like we're going to say that these are features that this is like a series of events that have been attached to a feature. So like a feature here might have been, B, C, D, E, and our event was A. And so at some point in time, A came along with the value of 0, and it looked up the feature, and it got the rest of the row. And that is how, that's our story for modelers. I mean, actually, I didn't really draw it like this. They'd probably be very sad about it, and they probably hate all this applicative functor stuff anyway, but just kind of, force it on them, But that's basically the story, right? So we're using that feature abstraction to build these matrices. And once you've got the matrix, as I mentioned, we've got to solve problem, right? Then you can throw it at scikit-learn, TensorFlow, et cetera. So what does it look like? So it's kind of vague. We're going to go in a little bit more. So here's the Scala code of kind of what it looks like. So we have basically two objects, as I mentioned, an event and a feature. And somebody kind of told me, and I kind of guess I agree with them, that event was maybe a bad name for the first thing because it's really representing a series of events. So it's but whatever. Imagine it as the full history of this event, the event of click, the click event. So it has many inside, but you can't do too much with it. So think of them things that pop out of Kafka or whatever at some point in time. Now, this is basically the only thing you have. Actually, you could have represented it in terms of a fancy concat map. But you can map it onto, you can get the time that event happened and change it, and maybe I need to decorate it, and if, I can do some transformation that's time aware. I can expand one object into many or 0. And then some of the rest of them kind of fall out of that. I can merge two streams together if they're the same type. So this is kind of a combinator. It's a monoid, right? It's a monoid because we can make an empty event stream, no events ever happen. That's pretty simple. And we can merge streams together. And this is one difference between the classical literature on FRP and what we chose to do. Sometimes in FRP, you say that each event stream can only have exactly at most one item at each point in time. In practice, in a real system, there's no way to guarantee that. You may have many front-end machines that are consuming events, and we relax that, and we allow many items to appear at a point in time. And a feature is relatively simple. It's something that we can change the value, and we can glue two of them together. Now, I don't think I jumped up and down about this yet, but I probably should have earlier. Features, unlike what we saw in the paper, where you have behaviors that have values, in reality, features are about something. So we have features about a tweet. We have features about a merchant. You can have features about a user. And so we explicitly expose that in the API. That the K here is what is the feature about. So notice that we can't really change what it's about once we make it. We can change the value of the feature, though. We can, if you give me a feature, well, we'll see some examples in a moment. So this is the basic API that we have. And this is pretty much all our customers need to learn. These are the people who are actually building models. So in it, we got to get our type classes on. Let's go. So event is actually a functor. It's actually something slightly above a functor. And I tried to get people in cats to get into this, but they're it's you can lead people to water, man. But whatever. So there's something above a functor, but below a monad or below applicative, where that both Spark, Scalding, lists, vectors, this event, they all share, is the idea that you can kind of you can merge them together, you can map them, and you can expand one item into 0 or more items. So there's a type class there that could be very useful in data engineering because we could write code against it that would apply to many of these things. But so far, I haven't sold that yet. So if you're interested in that, dig up that cat's PR and say, yeah, I get it now, Oscar. We actually probably do need that type class. Anyway, this one is applicative. So we can join two of them together. So what do these mean in practice? So applicative is like a functor with a little bit more. And functor is just something in Scala world that we can map on. We can definitely map on this thing. We can map the second column. We can't change what it's about. Feature about me is still about me after we change it, but we can change what it might, the value it might have. We could say, one feature about me is how many pets I have, but I could change that. I could map that into do I have 0 or more pets, right? I don't need to do any fancy computation there. I could just say map if greater than 0, true, else false, right? That's not really what you want to do. But what's really cool is the combinators, right? So how can we glue together features with events, or events with features, or events with events? And you have a little bounded set of things you can do to glue these things together. And then it gets pretty cool. So the cool thing here is that time-aware join problem, you just can't even express bad code. So that's the cool thing. So there's a lookup notion. I can make a new event from an old event and a feature. But notice time doesn't show up here. So I don't say I look it up at last Tuesday. The system only can express that you can only look up a feature as of kind of now from the point of view of the event as it happens. And there's no thing that a user has to do or can even express that can get this wrong. So that's I think one of the best features that the system has. Probably the best feature. The other thing is well, where do these features come from? I mean, I don't know if you looked at the previous page. I hope you were asking that because constant features is pretty boring. If you can only make constant features and glue them together and map them, that doesn't sound like you'd be doing too fancy machine learning here, man. So, so the cool things that you can do to create features are, a very common one is I want the latest value of an event. So an example of that is a tweet might have, we might want a feature about a tweet, and we could say the last time it has been viewed. Who is the last user who used it? That's a very simple thing to express. You have a series of events of viewing tweets. You have the tweet ID. You have the user that viewed them. And now you can see who is the last person at any given time to view a particular tweet. So that you just express that this way. That's all you can say about it. You can't do more. You can't, that's just what it has. The next thing is, and I can't stop forcing people to express computations in terms of monoids. And I wasn't about to stop in my new position at Stripe. So the other thing that you can do to create features is to take a series of events that have some value v and just sum them up. In fact, the original FRP paper has a notion of this as well. They have an integrating feature that is kind of nice for mouse movements and things like this that they were drawing, which was pretty cool. Again, we already mentioned product, the ability to glue two things together. That's another combinator that you have, and I didn't call it out again, but you can also combine events with themselves. So you have this 2x2 matrix. Events can be combined with events, features can be combined with features, and events can be combined with features in different ways. Any questions about this? Cool. So, also, people love the free, right? So last year was the year of free, I think Rob Norris said, so we got to get our free on. So actually, in fact, when we were building the system, people were impressed. They're like, wow, the basics of your system, you were able to get it working for us to use so fast. That was pretty cool. And the secret is we didn't actually do anything. The secret is the implementation is that these are just these free things that I described. So our implementation doesn't do anything. It just describes the business logic. So you actually just build up their sealed traits, or actually they may be abstract trait, whatever. Anyways, they're sealed. People can't subclass these and make their own or program them in fancy ways. They just can't do that. It's just a way of telling me describing your logic. That's all it is. So that's all the users can do. They just build up this free thing. Now they can't talk about anything outside of the world, right? So they can, do we talk about how to, I don't think the only way you can get into it is this function here. This is the only external way to get in. And all it does is say, like, I have a source of type A, and like I give it an identifier. But that doesn't like give me the data. That's just like a thing that you can have and like make graphs with and, you know, traverse and stuff like that, you know. So that was it. So event is like your free functor, and the feature is just a free applicative for the most part. And we have these special combinators, you know, all the things that you see, they're just case classes. You know, how do you implement like a product and feature? It's no problem. Case class, product feature, boom, you're done. You know, it's like one line of code. Map, same thing. How do you implement map feature? You got a case class of map with a function. You're done. It's easy. So once we've got that, we can, well, you know, I don't know. Like we'll talk about what we're going to do in the end. But what this gives us is our feature engineers are like 100% dealing with business logic. There's like 0% systems like concepts in this API. So they can define with zero dependencies if they wanted to, just define the business logic of creating very, very complex features. And that's pretty cool. Now, once we've got that, we can have various interpreters and compilers to like compute them in any number of ways. But we've constrained the system so much that it's very simple for us to do that. Basically, we just have to, someone has to provide us the right inputs, and then we have like, you know, a rich enough palette for you to make very, very cool features, but constrained enough for systems people who like to geek out to actually like schedule this effectively. By the way, I think this is like one of the biggest deals in building systems of abstraction is like finding like how much can you tightly limit things so that someone can barely express what they need, but the systems people can go over and actually efficiently execute it. And I think that's like, it's a really fun and been a productive area for people who like systems. And I think you can see so many examples of this. So let me just talk a little bit about like what these things do. Like, you know, some of you must be in the audience and not really wanting to talk about applicative functors and everything. So now I'm going to restate some of these actions in terms of the matrix that you might, like if you're thinking about feature engineering, they might make more sense. So what map does is all it does is if you have some column, if you have some way of producing a new column or columns from the old column, that is map. So if you're thinking about like some system that you might have worked with to produce, you know, that's what map gives you. Very, very common operation. Not weird that we have a functor for this thing. That's cool. I mean, a canonical example might be here. You have a feature of merchant and total charge count. And it might also have a total charge amount. Well, average is pretty trivial to derive from that, right? I could just divide the two. And I can produce that feature by doing a map and dividing it, right? Great. Feature.product glues columns together. So you might have one matrix and another matrix and the third, and that's exactly what we're going to build up when we're finally giving a big, fat, wide matrix to some training system. And that's what product gives you. So one way is that someone may have a really cool feature that computes the total charges amount in US dollars, and someone else may have some fancy hyperlog log powered feature that generates the unique cards that have been used with this merchant. And you may say, hey, actually, I think my model will perform even better if I can borrow your feature and put it all in one big model. And so to the user, it's really simple. You call .product, you say, now give me some training data, and it just all pops out. And it's like totally magical. It's great. Lookup is where we do some cool stuff. So now, I don't know if you noticed, there's a little bit of sleight of hand. In the original papers on FRP, you could ask things, the behavior, for what is the value at a given time. We actually don't expose this to the user. So it's kind of weird. It's like it's a little bit like the monad trick. You can get into the monad, but you can't get out, right? You know, it's like, you know, there's like not, you know. So the feature is the same way. We let you get into features. We don't actually ask you, like, there's no way that you can say, like, okay, but next Tuesday or last Wednesday, what was that feature value? That is not a method on this thing. It does not exist. So you have to understand that conceptually it's providing you something. It's providing you a model of how to compute, but it's not giving you, like, the ability to reach in. There's no unsafe I/O here, you know? So So you've got the feature, it conceptually exists, but maybe we're never going to compute it. Maybe we're just like very lazy about it and we don't need to compute all this. But these events can come in at certain times, and at those times what we tell you is that we could produce a new event stream that would tell you the events at those times. So that's what that lookup did. Lookup gave you event to feature back to event. So we can learn how to schedule that later, but that's what's going on. So this is what's very, very tedious to do by hand. This is that time-aware join. If you have a big pile of data, to look up E, you had to go back and say, okay, let me get all the data up to that point. What would the value of the feature have been? This is a real pain. Nobody wants to have to deal with this, and it's really easy to screw up. This is like the big value add. This is the takeaway of this system. So I call this property like temporal consistency. You know, it's like, I don't know what kind of time travel movies you like, but I like the ones where they loop back and like everything like still makes sense and you don't have to like worry about it. And like, you know, so like we're ready to go for modeling systems like that. We can't do the Bill and Ted's type, but we could do, or Back to the Future. Not going to work with this feature system. So here's an example, and I'm sorry, I'm like a bad guy. Like, it's like I like abstractions, and then I know a lot of people are like, yeah, like, but let me see an example, and like this is where I'm gonna fall down. And this is taken from one of our unit tests that like I think Eric Osheim wrote it because he's even better at like at least he has a dog and you know feelings for other animals. So like here you go. So this is actually from a unit test. So we've got events which are barks, jumps, and howls. And we can like make a feature that has a given dog barked or not. So we make that we map the barks. We can take the name of the barker. I actually didn't include the case classes of those three objects, bark, jump, and howl, but they have a name associated with them and like some metadata. So we gotta just take the name and then the value. I'm just gonna throw it away entirely because I just want a unit. Like I wanna see what happens. And then I take the latest value and I'm going to get an option. If you remember that combinator, the latest combinator gives you an option of the value. And all I care about is it defined or not? So that's like a real kind of feature, you know, cool. We can take the average volume of the howls and barks, like we're going to combine them together. So here we exercise some. And by the way, I lied to you earlier when I said that the methods names. So I catsified the names, but actually internally I algebraified the names, and we use sum for combine and zip for product. But like I don't know if whatever. So sum is actually like a mono. You're combining with the monoid, and I've talked about this in the past. Turns out, shocker, averaging can be a monoid. So we have this thing already. We can average the value of these things and combine them together, and we get the average value. And here's another way of computing that same one, which is actually pedagogically clearer, but from a numerical stability point of view, worse. That we could have just computed the average of the average value of the howls and the average value of the barks, product them together, and then combine. So this is like two ways you could have done it. Because it's a monoid, it doesn't matter which way you do it. So, and this is just a dumb unit test. It actually lives in our repo. And sorry that I don't have a sexier example. But that's like the challenge for you. Like what cool features could you make? So how do you actually run these things? So I've talked about very abstract. I said I didn't actually implement anything, which is like, you know, maybe underselling myself because it's all a free thing. Actually, what I said was that it was really easy to get the free structure. And then, because I put this talk in, I'm like, yeah, no problem. We'll like talk about it in November. We'll have all this like great like operational war stories. And I'm like, you know, as of like last night, dark reads were actually live. So, actually the backend turned out to be a massive pain in the ass. So we have several backends. The first one that we made was a little interpreter that can schedule this to like a Scala stream. So I'm eliding this code here of converting the event into a stream, but conceptually you can imagine I should be able to do that. So I can give a lazy stream with timestamps and events in the order in which they happen. And then if you give me a feature and a key that you want to look up and a timestamp, I should be able to give you the value. And you know, if you give me all the inputs as streams, I should be able to do this. And you know, it's pretty straightforward how you do it. You just kind of like case match on those sealed classes and go through and do the thing. So that was the first one we built, on which we can write unit tests locally. Our users can like, you know, make sure they're exercising their business logic with this. That actually has some use. Our second backend that we built for this was a MapReduce-like backend. So because of the structure of the combinators that we have, we can make it look like basically, and when I say MapReduce, I mean like the logical notion of MapReduce. So it's another AST, an intermediate representation that has like series of mapping operations followed by reducing operations. So that's like the model that Spark has or Flink has or any kind of data flow system has. So we have this intermediate representation like that, and we do the similar kind of thing. We actually get a little fancier there. It turns out with the structure of these things, you can always kind of imagine that there's like a free functor hanging on the back of these things. And that's kind of nice to like discard that free functor and like apply that at the very last minute. So we did some tricks of like you can convert features to unmapped features. This is like always something like the unmapped part along with its mapped part. That turned out to be useful for the building the compiler, but that's like our second backend. And our third backend was useful for real time. So then we had a third backend that is like a push backend. So in the push backend, we're planning it onto two objects. One that we call a multi-consumer. It can consume from different sources. You say source A just happened and here's the value for A, or the howls just happened and here is an example howl, and I can push it in and it's going to return me a nothing. I love it when I can work nothings into type signatures in Scala. It's like one of my favorite things, you know. And I also will give you a way to read that at real time, now. So you give me a key and a timestamp, and I'll give you the best answer for what the value is. And it's the same kind of trick. I don't really know what the takeaway of this slide was, except for the fact that we do, traverse is always the answer, So if you have a question, it's traverse. So that's pretty much it. So what we have here is, I think, a very minimal and principled API for feature engineers. And the principled nature of it is not just because we're like dogmatic, FP jerks. It's not just because of that. Like that's like a side thing. In addition to us being dogmatic FP jerks, it also means that the backend system has a lot of opportunities to optimize this and plan this in many ways. So we have 3 or 4, like the examples I gave. When I say the MapReduce backend, we actually can run it on Scalding and another system called Hummingbird that's kind of similar, but it would be like probably 100 lines of code to like run it on Spark. I mean, maybe 200. We just don't do a lot of it. It'd be very easy. And that's because of how constrained this model is. The next thing it's really awesome, and I think is like really important, is that it 100% separates the business logic from the implementation details. Like there's just no way to think about like even expressing things, like some forms of expressing things the wrong way. You can still write garbage features that aren't very useful or something, but like you can't do a pretty wide class of errors that can come up. And I mean, this is maybe a restatement of it. It frees the engineers, our feature engineers, from having to worry about temporal consistency because it's not possible to express like inconsistent temporally data in the system. That's like our favorite trick in FP, right? Like make errors inexpressible. I think we've actually accomplished that for this problem in this case. So that's all I've got. I think I've got some time for questions, if anyone has any.
So questions? We go over the mic. Yeah, so I have like 1.5 questions. So first, if we have like temporal data and we have a sliding window, so we're not, while aggregating we add something, but we have to also deaggregate, subtract something. So we'll need something bigger than to reduce, right? And the other approach would be like convolution, temporal convolution, where you have some kind of filter and you do that stuff. So I was do you plan to cover those kinds of actions?
Yeah, that's a good question. So if you go back and you look at what the API that we give to people to produce features out of events, they're a little bit limited. Like this one's pretty straightforward and like it's very useful. It comes up. But the second one, you require some way to combine values as the monoid. But the most common thing that doesn't immediately grab people as being a monoid is a windowing operation. So you might want to take the maximum value over a window, and it's non-trivial to express some of those kind of calculations as monoids. So let me answer there's several answers to this. Let me get the last one first, your question. Do we plan to support that? I think we may plan to support that. I'm still coming off of my experience and biases from engineering systems at Twitter, where like data rate was like really, like you're constantly drinking from a fire hose. So we were really struggling with that. Transactional data turns out to be much smaller, and I think a lot of people are dealing with smaller data, so you could kind of like relax things a little bit. So you can imagine a more general operation here than a monoid that might still give us a lot of the benefits, and we might think about doing that. The reason why we want to that we don't want to reach for that right away is the ability to combine this kind of Lambda architecture systems that a lot of people have built of combining batch and online stuff becomes very, very easy and tractable if you have a monoid, and it becomes very, very difficult when you have general windows. So that's one answer. The next answer is there are many things that are window-like that are monoids. So like one thing is that you just it's wasteful, but you could keep the value v could be like a fat memory that remembers the last week or something, and it means that it's expensive to go fetch and update, but it can be tractable. The other thing is that exponential moving average turns out to be efficient, but also a monoid, and several exponential moving averages can approximate a window very well for many things. So that's kind of the space of answers we give people when they always ask, and indeed I'm glad it was the first question. All the feature engineers always ask this, and that's what I tell them. I don't know how happy they are.
Any other questions? A couple over here.
Hi. I would like to ask you to extend a little bit about the compilers in terms of production code. What is the performance? Because I assume this lives on production already. And what is the P99 of your scoring?
Yeah, that's a good question. So we actually made a mistake when we were implementing this that I'm a little bit embarrassed about, which maybe I shouldn't even. I'm just some idiot like anybody, so I can tell you what a dumb guy I am. Okay, it's fine. So we were like, hey, we've already implemented things similar to this. We could just plan this feature framework to be something that's more constrained on top of a system that I built before called Hummingbird, and that could be cool. But actually, it turns out that was false, because this gives you, lookup is actually, it gives a consistency model that if that isn't what people expect, it's going to be inconsistent with the data. And systems like Storm, which are just tuples racing through systems, don't have this notion that they can kind of put a barrier someplace and make sure A happens before B. So we built the system, we built it on top of Hummingbird and Storm, and first of all, we didn't like the latency numbers. And for the system that we were prototyping it for, we want latency on the order of we had a budget of something it's, if you're running transaction, if anyone uses Stripe, you might notice that you're willing to wait a second for a transaction to happen. So the transactions windows are pretty long. So we were given it would be fine if it took 300 milliseconds on the outside even before things came in. It turned out we had trouble meeting that end-to-end with Storm by itself, and it was inconsistent because of this racing issue of tuples racing through. A data flow without synchronization barriers is not what people actually want. So we then had to, and that's part of the reason we were somewhat delayed, we decided to build this directly as a Kafka consumer. So the third platform that I mentioned that reads this, it basically just sits in a loop, reads some events from Kafka, and then transactionally, all or nothing pushes you through the whole feature. Now that can be actually extremely fast. So for very simple features, it might be simple features meaning maybe you only have 3 round trips of talking to different materialized views of part of the feature. That might be 10, 15 milliseconds. And for really, really complicated features that have more 15 or something, a much larger graph, it's still less than 50 milliseconds for the cases that we see. And that's actually been really, really fine for us. So my regret is that we didn't just go directly to on top of Kafka first. And I wonder now if we can throw away the monoid restriction and just go with try to get it to an exactly one system only built on Kafka. That might actually work for us, or at least be a possible backend. So, I think Ken had a question. I want to make sure he has a chance to ask it. Do you have a question?
So typically, a lot of the time spent in these systems is none of the cool, sexy stuff you're talking about. It's like the data cleansing you need to do, and you're not worried about any of that.
Right, so that's a good question, yeah. I mean, worried about it, I mean, I'm worried about it. I mean, I don't know about...
But you weren't trying to address any of that aspect of the data pipeline.
I think the main problem, the main problem we were trying to do is combine many sources together in one consistent view. But each of those sources, they still might be very dirty or ugly, and we haven't tackled that part of the problem.
Okay. And can you actually show us any real code?
I really can't show you any more than the code that I got there. Sorry, I probably can't. There are some really fancy stuff, but like, I mean, of course, like we do fraud models, right? And like it's really important for us probably not to broadcast anything that goes into like what are fraud features. So I really can't do that. But I'm available. Please come talk to me. Thank you for attending my talk. Thank you to my team. Travis Brown is here. He's worked very hard on this. Eric Osheim worked very hard on this, and Sam Ritchie. He worked some, you know.